This section explains the basic concepts of decision theory and how it reframes what classical statistics is doing. Classical statistics infers theta without asking what the inference is for. Decision theory makes the use constitutive. The frame has three parts. There is an unknown state of nature, theta. There is an action, drawn from a menu. And there is a loss written L of theta and A that prices each pairing of an action with a world. The chosen act is the one that minimizes expected loss. Two pieces of information beyond the sample feed this choice. The first is consequences, which is the loss. The second is prior belief about theta. Savage gives three identical experiments: the tea-tasting lady, the music expert, and the drunk calling coin flips. Each one rejects the hypothesis that beta equals 0.5 at a significance of 2 to the negative 10th power. Yet prior plausibility forces three different verdicts. The same data yields divergent conclusions. The chapter installs that vocabulary and the pivot from inference about theta to the best action under uncertainty about theta. This pivot is the reframe the whole book rests on. This first concept explains why statistics does not end at an estimate and why inference is only a means to an end. Statistics stops too early when it stops at an estimate of theta. Berger's opening move relocates the terminal object. The output is an action, and inference is merely instrumental to choosing it. Three independent channels compose into that choice. The first is the sample, the data bearing on theta. The second is the loss, written L of theta and A, which is what each wrong action costs. The third is the prior, what was known before the data arrived. Classical inference uses only the first channel and reports theta regardless of how it will be used. Decision theory subordinates theta to the action that minimizes expected loss. Bayes folds in the third channel the prior. Savage's triple makes the force of the prior vivid: the tea lady, the music expert, and the drunk friend. The likelihood is identical across all three, yet the conclusions come out opposite. This shows the prior is structural. It is part of the machinery that produces the conclusion. This section explains where value comes from and why it must be defined through ranking rather than measured directly. Value is recovered from a preference order rather than read off an outcome. The ranking comes first, and the number follows from it. The hinge of the chapter is that nominal scales lie. The second $100 is worth less than the first. A sure $10,000 is chosen over a fair gamble on $25,000. So no consequence carries its own number. The repair inverts the dependency. Assume only that you can rank lotteries, then seek a function U on rewards whose expectation reproduces that ranking. The statement is this: lottery P1 is ranked below lottery P2 if and only if the expectation of U under P1 is less than the expectation of U under P1 is less than the expectation of U under P2. Utility is fixed by what it represents rather than built from substance. This is a representation theorem, the same defined by its action move that Yaneda makes. Loss is then merely negated utility, the quantity the rest of the book sets out to minimize. This section explains how a preference ordering becomes a number. A preference ordering by itself carries no number, and the chapter's move is the representation theorem that manufactures one. Start with preferences over probability distributions on rewards. The theorem finds a utility function, u, such that the second distribution is preferred to the first exactly when the expected value of u under the second exceeds the expected value of u under the first. The qualitative order is recovered by a single scalar. The two opening puzzles make the case for why this is needed. The millionth dollar is worth less than the first. The sure $10,000 beats the fair gamble on $25,000. Read carefully. These are not pricing anomalies. They are evidence that monetary scale and value come apart, and utility is the corrected scale. Loss, the object, the rest of the book minimizes, is then merely negated utility. The chapter exists for one purpose: to ground decision-making in a cardinalization of mere preference. This part explains where the prior distribution comes from. The unknown theta is not random. The smoking proportion either lies between 0.3 and 0.35, or it does not. Yet the whole Bayesian apparatus needs a distribution over it. The chapter's single job is to earn that distribution by severing probability from frequency and rebinding it to degree of belief. The probability of an event E becomes the relative likelihood that introspection assigns. Equivalently, the stake at which a bet on E is fair. This is what licenses pi of theta, the third primitive, beside the likelihood f of x given theta and the loss L, as a legitimate object the later machinery can condition on. Berger's recurring posture already surfaces here. Distrust the grand intuitive leap. Break the problem into separately elicitable components and let the mathematics of decision theory recombine them. This section explains how a probability can record a degree of belief instead of a frequency. Probability need not count repetitions. It can measure a commitment. Take the smoker proportion, theta. It is a fixed number either inside the interval from 0.3 to 0.35 or not. There is nothing random about it. Yet you can still write that the probability that theta lies between 0.3 and 0.35 equals 1/2, because that number quantifies how you would bet, rather than how the world 0.35 equals 1/2. This single inversion, from frequency in the world to belief in the observer, is what licenses a prior pi of theta. The chapter's job in the book's arc is to manufacture that input, the thing Bayes later turns against the data. Berger's operational caution rides underneath. Distrust the grand intuitive leap. Decompose belief into simple, pairwise comparisons and let probabilities algebra recombine them, never eliciting the answer whole. This section explains the single structural move that generates Bayesian analysis as a complete paradigm. The unknown parameter theta gets a probability distribution of its own. That single move generates the entire paradigm. Once uncertainty about theta is itself probabilistic, Bayes' theorem conditions the prior written pi of theta on the data, turning it into the posterior. Every inference and every decision is then read off that one object. Credible sets are literal probabilities that theta lies inside. Hypothesis tests report believed probabilities of the hypotheses. Optimal actions minimize posterior expected loss. Berger frames this as the book's only self-contained paradigm. Later chapters patch frequentist special cases. This one stands alone. The 7 justifications converge on the sharpest of them, coherency. Any preference, ordering satisfying mild rationality axioms, is forced to be Bayesian. So the question shifts from whether to be Bayesian to which prior to use. This section explains the single move at the heart of Berger's 4th chapter and why that one move makes the chapter self-contained. Berger's fourth chapter turns one move into an entire paradigm. Stop treating the unknown theta as a fixed constant that the data merely points at, and treat it instead as random. Give it a prior, then condition it on the data. The posterior that results, written pi of theta given x, is itself the answer. Every inference and every decision is just a functional read off that one distribution. A point estimate is one such read. A credible set whose stated probability genuinely is the belief that theta lies inside it is another. So is a test that reports the probabilities of the hypotheses themselves. What makes this self-contained, unlike the chapters that follow, is that inference and decision stop being separate machineries. Both collapse into operations on the posterior. The generative seed is this: invert the conditioning, and the rest is bookkeeping. This section explains minimax analysis as a decision rule and where its justification holds. Minimax is the rule you adopt when you assume the world is out to get you. You fix the worst state of nature, then act to minimize that worst-case loss, the infimum over decision rules, delta of the supremum over states of nature, theta of the supremum over states of nature, theta of the supremum over states of nature, theta of the risk, r of theta and delta. The principle is correct in exactly one setting, when nature genuinely is an intelligent opponent, maximizing your loss. So game theory is its native home, and it inherits von Neumann's saddle point. Set against Chapter 4's Bayesian rule, minimax carries no axiomatic justification. Neutral statistical nature bears you no malice, so minimax survives only as deliberate conservatism or as a robustness yardstick. The Bayes rule, whose prior concentrates on the worst theta is the most prior concentrates on the worst theta, is the most prior robust rule available. This is gamma minimax, where gamma minimax, where gamma minimax, where gamma is the set of all priors. Berger apologizes for the chapter. Its prestige is mathematical richness, not rationality. This part explains the one move that survives when you strip the prior away. Stop averaging over nature's states and instead play against nature as a malicious opponent who will pick your worst case. That single substitution generates the whole chapter. Where the antagonist is genuinely intelligent in the Borel and von Neumann game theory of section 5.2, minimax is simply correct. Where nature is neutral, it becomes a posture rather than a theorem. Berger concedes that minimax violates the very rationality axioms that forced Bayes in Chapter 4, so it earns its place. Only axioms that forced Bayes in Chapter 4, so it earns its place only as the robustness limit. Minimaxity is gamma. Minimaxity over the class of all priors. The Bayes rule against nature's worst-case prior. The chapter is what you do when you refuse to name a prior. This section explains how a symmetry in a decision problem shrinks the space of admissible rules. A decision problem carries a symmetry. Measure an exponential decay time in minutes instead of seconds, and the formal structure, the densities, the parameter space, and the loss returns identical. Demand that the rule respect that symmetry, and the admissible rule space collapses. In Berger's example 1, the functional equation delta of x equals 1 over c times delta of cx forces delta of x to equal k times x. That is a single free constant where a provably best choice exists. That is the whole move. A group acting on the problem quotients the rule space down. Here is the surprise: the chapter keeps quiet. This equals Bayes under the prior. That same group fixes the right Haar measure, Here, the non-informative scale, prior, pi of theta equals k over theta. Symmetry silently chooses the prior. This section explains how a symmetry of a decision problem can pick out the estimation rule by itself. Start with the symmetry. If you rescale the units, seconds into minutes, the chosen rule must stay unchanged. Demand that the estimator commute with the whole group of such relabelings, the scale group, which is Berger's. Example 1. That demand collapses the admissible rules down to a single one-parameter family, delta of x equals capital K times x. Risk then fixes the value of capital K times x. Risk then fixes the value of capital K. Symmetry alone names the rule. The generative move here is equivariance as a fixed point constraint. A rule is what survives the group's action on the problem. The boundary that exposes this structure comes from. Example 2. Restrict a parameter space. The symmetry breaks and the determination evaporates. The rule is no longer pinned down. The chapter's understated payoff is the identification at the end. This best invariant rule is exactly Bayes against the non-informative prior, the right invariant Ha measure. This section explains how pre-posterior and sequential analysis lift the decision one level up. Every prior chapter took the data as given and optimized the act. This one moves the choice upward, so the experiment itself becomes the thing decided, and the book restricts that vast design space to its sharpest case. When to stop sampling? The move is to fold sampling cost into the loss, so two opposed quantities balance. More data lowers decision loss, but more data raises experimental cost. Sequential analysis then makes sample size endogenous, a random variable the evidence determines with a stop or continue decision after every observation. The lot inspection anchor carries it. 50 clean items already settle the question, so paying for the fixed 100 is waste. You gather exactly what the decision needs. This section explains how Chapter 7 lifts optimization from the action to the experiment that produces the data. Everything before this chapter optimized the action given a fixed body of data. Chapter 7 lifts the optimization one level to the experiment that produces the data chosen before any data exists. That is why it is called pre-posterior. The generative move introduces a second cost, sampling, which now opposes decision loss. More observations shrink the loss but inflate the cost, and the optimum balances the two against each other. The elegant case is sequential, where the meta-choice, observe once more or stock, is itself a Bayes decision. It is recursively the same machinery applied to a stopping rule rather than to a terminal action. That recursion is the whole chapter. Design collapses into deciding when to stop deciding, so you gather exactly the data a target accuracy demands. Never. Wald's wasted final 50. This section explains how to shrink the space of decision rules before you optimize, and what the two notions of completeness buy you. Before optimizing, shrink the search space to its acceptable frontier. A class is complete when every rule outside it is strictly dominated by one inside. Nothing optimal can live outside, so you discard the rest without loss. Essentially, complete relaxes domination to allow ties, what is called R equivalence. It is a strictly smaller class, bought by keeping equivalence rather than only strict improvements. That is why reducing to a sufficient statistic or to non-randomized rules under convex loss lands here. The minimal complete class, when it exists, is exactly the admissible rules. Completeness and admissibility collapse onto one set. That is the chapter's whole function in the book's arc. It converts an intractable search over all decision rules into a search over this pruned frontier. This part explains why a decision rule search can be confined to a small, provably sufficient subset. Never search the whole space when a small piece of it provably contains everything worth keeping. A decision rule is wasteful if some other rule beats it everywhere. The chapter's move is to pre-filter, to find a subclass, call it the class phi, such that any rule outside it can be matched or beaten by a rule inside it. 3 terms carry the structure. Complete means strictly beaten. Essentially, complete means matched or beaten. And the minimal complete class collapses to exactly the admissible rules, the irreducible survivors. Once you have it, every later search, whether Bayes or Minimax, runs over the small set, not the monstrous one, with no loss. This is the same structural gesture as a basis, a sufficient statistic, a generating set. Replace a space by a subspace that throws away only the dominated.